20 horsepower motor operating at 208 volts, three-phase, may present two different wiring diagrams. Understanding these diagrams is crucial for proper motor operation. The diagrams typically illustrate connections for both low voltage, which is the 208 volts configuration, and a high voltage configuration. Focus will be on the 208 volts, three-phase connections. One diagram connects the lines directly to the motor terminals, whereas the other connection method creates a delta configuration inside the motor windings. Examining the diagrams, the first diagram, often recommended for standard use, directly connects the three phases, lone, L2 and L3, to specific terminals on the motor. The typical connections are lone to terminal 7, L2 to terminal 8, and L3 to terminal 9. In this configuration, additional connections link terminals 6 to 12, 4 to 10, and 5 to 11. This is a straightforward approach that prioritizes efficiency. The second diagram presents an alternative connection method. Here, the connections are lone to terminals 12, 6, and 7, L2 to terminals 10, 4, and 8, and L3 to terminals 11, 5, and 9. This configuration introduces a delta connection within the motor windings. This delta connection serves to increase the starting torque, meaning the motor can overcome higher initial loads when starting. However, this higher starting torque comes at the cost of reduced efficiency during continuous operation. For most general-purpose applications, using the first diagram is the preferred method. It provides a direct connection that ensures the motor operates at its designed efficiency. The motor will run more economically and in normal load conditions. If the application demands a high starting torque, like a pump that needs to start against a significant head pressure, then the second diagram might be the better option. The increased starting torque, approximately 1.732 times higher, can help the motor overcome these demanding startup conditions. However, it's crucial to consider the trade-off in efficiency during continuous operation. Before making any connections, ensure that the voltage and frequency of the power supply match the motor's specifications. This information is typically found on the motor's nameplate. Double-check all connections before energizing the motor. Incorrect wiring can lead to damage to the motor or create a safety hazard. It is recommended to consult the manufacturer's instructions for the specific motor model. These instructions provide detailed information about wiring and any special considerations. When deciding which diagram to use, the primary consideration is the application's requirements. If efficiency is paramount, use the direct connection method. If high starting torque is needed, then use the delta connection method, understanding the efficiency implications. Choosing the right wiring diagram is critical for ensuring proper motor performance. Consider the application's requirements, prioritize safety, and consult the manufacturer's instructions. Ensure the voltage and frequency of the power supply match the motor's specifications. Always double-check the connections before energizing the motor. The increased starting torque of the delta configuration comes at the expense of lower operating efficiency. Firstly, if the application involves frequent starts and stops under heavy load, the delta configuration may be beneficial despite its reduced efficiency. Secondly, if the application involves continuous operation under relatively constant load, the direct connection method will generally be more cost-effective over the long term due to its higher efficiency. Thirdly, it's important to monitor the motor's temperature during operation, particularly when using the delta configuration. Excessive heat can indicate overloading or other problems that could damage the motor. Understanding the characteristics of each wiring configuration allows for an informed decision based on the specific needs of the application. For a 20 horsepower motor, the difference in efficiency between the two wiring configurations can be significant, especially over extended periods of operation. While the delta configuration provides increased starting torque, it also draws a higher starting current, which can put a strain on the electrical system. In some cases, it may be necessary to use a soft starter or other motor control device to limit the starting current and reduce the stress on the electrical system. The direct connection method, on the other hand, draws a lower starting current and is generally easier on the electrical system. However, it may not be suitable for applications that require high starting torque. Consider the impact on the electrical system when choosing between the two wiring configurations. If the electrical system is already heavily loaded, the direct connection method may be the better choice. If the electrical system has plenty of capacity, the delta configuration may be acceptable, provided that the starting current is within acceptable limits. Review the motor's nameplate for specific information about the motor's voltage, frequency, horsepower, and full load amps. This information is essential for ensuring that the motor is properly connected and operated. The nameplate also provides information about the motor's insulation class, which indicates the maximum operating temperature of the motor windings. It's important to ensure that the motor's operating temperature does not exceed the insulation class rating, as this can damage the motor windings and shorten the motor's lifespan. When connecting the motor, use appropriately sized conductors and ensure that all connections are tight and secure. Loose connections can cause excessive heat and voltage drop, which can damage the motor and create a safety hazard. Consider using a torque wrench to tighten the connections to the manufacturer's specified torque. This will help ensure that the connections are tight and secure, but not over-tightened. Over-tightening can damage the connections and create other problems. When selecting a motor control device, such as a motor starter or variable frequency drive, ensure that it is properly sized for the motor's horsepower and full load amps. Using an undersized motor control device can damage the device and the motor. An oversized motor control device is generally not a problem, but it can be more expensive. Consider the environmental conditions in which the motor will be operating. If the motor will be exposed to moisture, dust, or other contaminants, it may be necessary to use a motor with a totally enclosed fan-cooled enclosure. If the motor will be operating in a hazardous location, it may be necessary to use a motor with an explosion-proof enclosure. Choose a motor that is appropriate for the environmental conditions in which it will be operating. Properly maintaining the motor can extend its lifespan and prevent costly repairs. Regularly inspect the motor for signs of wear and tear, such as cracked insulation, loose connections, and excessive vibration. Lubricate the motor bearings as needed, following the manufacturer's recommendations. Keep the motor clean and free of dust and debris. By following these tips, one can ensure that a 20 horsepower, 208 volts, 3-phase motor is properly connected and operated for many years to come. Remember that consulting with a qualified electrician is always the best course of action if there are any questions or concerns. A qualified electrician has the knowledge and experience to ensure that the motor is properly connected and operated safely. When in doubt, always consult with a professional. If the motor is equipped with thermal overload protection, ensure that the overload protection is properly set for the motor's full load amps. The overload protection will protect the motor from damage in the event of an overload condition. The overload protection should be set to trip before the motor windings overheat. If the overload protection trips frequently, it may be necessary to investigate the cause of the overload and take corrective action. Do not simply reset the overload protection without addressing the underlying problem. This could damage the motor. If the motor is connected to a variable frequency drive, it is important to properly program the drive for the motor's specific characteristics. The drive needs to know the motor's voltage, frequency, horsepower, full load amps, and other parameters. Failure to properly program the drive can result in poor motor performance or damage to the motor. Refer to the drive manufacturer's instructions for specific programming information. When troubleshooting motor problems, start by checking the power supply to the motor. Ensure that the voltage and frequency are within acceptable limits. Use a multimeter to measure the voltage at the motor terminals. If the voltage is too low or too high, it may be necessary to adjust the power supply. Check the motor connections to ensure that they are tight and secure. Loose connections can cause voltage drop and overheating. If the motor is equipped with a capacitor, check the capacitor to ensure that it is functioning properly. Faulty capacitor can cause the motor to run poorly or not start at all. A simple test is to use a multimeter. If the motor is making unusual noises, it may be necessary to inspect the motor bearings. Worn or damaged bearings can cause excessive noise and vibration. The bearings may need to be lubricated or replaced. If the motor is overheating, it may be necessary to check the motor windings for shorts or grounds. A shorted or grounded winding can cause the motor to draw excessive current and overheat. Use an insulation tester, also known as a megometer, to check the insulation resistance of the motor windings. If the insulation resistance is too low, the motor may need to be rewound or replaced. Remember that electrical work can be dangerous. Always disconnect the power supply to the motor before working on it. Use appropriate safety equipment, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, consult with a qualified electrician. When replacing a motor, be sure to choose a motor that is the same size and type as the original motor. Using a motor that is too small can result in poor performance and premature failure. Using a motor that is too large can waste energy and increase the cost of operation. Match the replacement motor. Before installing a new motor, inspect it carefully for any signs of damage. Check the motor windings for shorts or grounds. Check the bearings for excessive noise or vibration. If the motor is damaged, do not install it. Return it to the supplier for a replacement. When installing a new motor, be sure to properly align it with the driven equipment. Misalignment can cause excessive vibration and wear on the motor and the driven equipment. Use a laser alignment tool to align the motor. After installing a new motor, test it to ensure that it is operating properly. Check the motor voltage, current, and speed. Listen for any unusual noises. Monitor the motor temperature to ensure that it is not overheating. Document the installation and testing process. This will help with future troubleshooting and maintenance. Keep records of all motor repairs and replacements. This information can be used to identify trends and prevent future problems. Establish a preventative maintenance program for the motors. This program should include regular inspections, lubrication, and cleaning. A well-maintained motor will last longer and operate more efficiently. When disposing of a motor, be sure to follow all applicable environmental regulations. Some motor components, such as capacitors, may contain hazardous materials. Dispose of these materials properly. Consult with a qualified waste disposal company for assistance. By following these guidelines, one can ensure that motors are properly installed, operated, and maintained for many years to come. Remember that electrical safety is paramount. Always take precautions to protect oneself from electrical shock. When in doubt, consult with a qualified electrician. The information provided is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician before performing any electrical work. This information is based on generally accepted electrical practices and may not be applicable to all situations. Local electrical codes and regulations may vary. Always comply with all applicable codes and regulations. The presenter assumes no liability for any damages or injuries resulting from the use of this information. Use this information at your own risk. The presenter material focuses on the technical aspects of wiring a 20 horsepower, 208 volts, three-phase motor. The two wiring diagrams presented offer different characteristics in terms of starting torque and efficiency. The direct connection method is generally preferred for most applications due to its higher efficiency. The delta connection method is suitable for applications requiring high starting torque, but it comes at the cost of reduced efficiency. Always prioritize safety and consult with a qualified electrician when working with electricity. And remember, while this discussion centers around a 20 horsepower motor, the principles can be applied to motors of different sizes, but always consult the motor's specific documentation and a qualified electrician.